Okay, great. So I think the Elvira is ready. So today, thank you very much for coming. We have very interesting talk. Uh, the title is "How can the ionosphere help in improving tsunami early warning system?" To be given by Elvira Astafyeva at the IPGP in Paris. But before her talk, let me tell you why this series. Because most recently at the AOGS, the Asia Oceania Geoscience Society um, meeting, we have a group of people who have the idea of organizing one would say a large-scale international cooperation with some focus on the Asia Oceania region for early warning system. It started by some space scientists because they think that the atmospheric research could help. On our hand, if we go on with this project, it would cover not just the satellite part, but also the ground-based measurements, also the ocean-based measurements. So it would be a very interesting large-scale project. But then today we have Elvira talk about the atmospheric signature, which is an important part of the story. So please, Elvira. By the way, she will introduce herself.
So, okay, thank you for inviting me, and thank you for the introduction. I'm very grateful and honored to be here. So my talk will be indeed about the ionosphere and how the ionosphere can help in improving the existing tsunami early warning systems. So indeed, before I start my presentation, just a small, introduction about myself, because we noticed that there was a couple of mistakes in the CV that was running on the screen. So I had to do very fast lines about my career steps, and I see some orthographic mistakes. Yeah, so I made my PhD with a professor under supervision of Professor Afremovich at the Institute of Physics of Soil Terrestrial Physics, which is in Irkutsk in Siberia, the Siberian part of Russia. So then in 2007, I was lucky to get the GSPS funding, and I worked at Hokkaido University in Sapporo, Japan, under supervision of Professor Heki. And in 2009, I moved to France to work at the IPGP, which is a French abbreviation for the Institute of Physics of the Earth in Paris. And I worked under supervision of Professor Philippe Lognonnet. And since 2012, I am a permanent researcher hired by CNRS, which is a French National Center for Scientific Research, and I'm affiliated since then at the IPGP. So currently I am a senior research scientist. I hold a position that is equivalent to a full research professor, always at the IPGP. So now back to tsunamis. So it's a Japanese word, which means harbor wave. Most tsunamis are generated by submarine earthquakes, and sometimes, much rarer, they can be generated by submarine volcanoes and landslides. So for the tsunami warnings, so mostly when we talk about submarine earthquake, when an earthquake occurs, what we need to know is whether a tsunami was generated by this earthquake or not. And this is called tsunamigenic potential. And to estimate that, we need to know in near real time. And by that, I mean as soon as possible. We need the information about the vertical displacements of the ground or the seafloor, what the dimension of this displacement, which part of the ground was shifted due to this earthquake, and we need to know the location of this displacement. And it's actually very difficult and I would say very challenging to have this information, especially for larger earthquakes in near real time. So what is possible to estimate in near real time very rapidly from seismic measurements is the magnitude and the epicenter position. But the epicenter doesn't always collocate with the source of the tsunami, with this vertical displacement. And here I would like to show the example of the Tohoku earthquake that occurred in Japan in 2011, the old one, but still very good example, where you see that the epicenter is shown by the star was about 150 kilometers away from the co-seismic displacement that caused this measured tsunami. So having this information about the source is very challenging, and we are facing several fundamental challenges. So with respect to this tsunami source, modern techniques, and I'm mostly referring to seismogeodesy that made an enormous step forward in near real-time imaging and estimating the source. But still, for large earthquakes with magnitudes more than 8, it is still very challenging to have reliable estimates in near real time. And 8+ earthquakes are those that will produce the largest tsunamis as well. So yes, I'm forgetting to say that an earthquake should not be strike steep. So tsunami will be mostly generated by earthquakes that produced significant vertical displacement, either uplift or subsidence. And strike steep earthquakes with horizontal movements, they don't generate large tsunamis. So then another challenge with respect to tsunamis themselves, when they are generated and propagating across the ocean. So already we do not know much about the source, but then tsunami is generated, and we could have monitored the propagation of the tsunami either from space or from ocean surface instrumentation. But most of so we don't have satellites, and systems like DART remain very expensive and very difficult to maintain. So most of tsunamigenic areas, they are not equipped with this kind of instruments. And finally, the existing tsunami warning systems cannot deal with tsunamis of other origin than seismic one. So for instance, in the case of the 2022 eruption of the Hunga Tonga volcano, that was an underwater volcano, the system said there was an eruption, the probability of a tsunami being generated is very high. However, it's not possible for us to make any forecast. We can estimate roughly the propagation of the tsunami, but we cannot give any reliable forecast about this tsunami. So what happened in the end is that this extraordinary event, the eruption of the volcano, underwater one, it generated 2 tsunamis. One was very extraordinary. It's one that we almost nearly observed for the first time, that was driven by the lump wave and arrived much faster than any other tsunami could, and provided a lot of casualties. And there was another tsunami that was a normal one that was much slower. So there are several challenges to face to improve. Things to improve, and this is where we suggest that the ionosphere-based methods, which mean the space-based methods, can help. So first of all, I don't know how much you're familiar with the ionosphere. Just a quick reminder, because ionosphere is a layer of charged particles that is located between 60 and 1,000 kilometers of altitude, roughly. It's a very variable medium, and mostly the maximum of the ionization, which is a very important parameter, is located between 250 and 400 kilometers. So this is the region where we will see our disturbances the most. So then ionosphere will be perturbed by different geophysical phenomena. So geomagnetic storms, thermosphere circulation, but also it will be disturbed from below. So such natural hazard events as volcanoes, earthquakes, and tsunamis will generate acoustic and gravity waves that will propagate upward and will reach the ionosphere in some time. And there we will detect them by using mostly GNSS receivers, and we need dual frequency receivers, and we will measure the total electron content. So the acoustic waves will be generated by earthquakes and explosions and some other rather rare events that is a sudden forcing. So they will have a very particular waveform, which is N wave, as you can see here. And because they propagate very rapidly vertically, so they will reach the ionospheric altitude in about 7 to 9 minutes in near epicentral area. So we call these disturbances coseismic ionospheric disturbances. Then tsunami propagating across the ocean will generate gravity waves. They will propagate obliquely. And because they have a much smaller component, vertical component of velocity, they will reach the ionosphere much later. It can take up to 60 minutes. So the time is still under debate. Yes, so one other, we will call these disturbances called tsunamic ionospheric disturbances, and they will have this more common waveform that we call quasi-periodic waveform that can be observed in the ionosphere quite often. Then about the volcanoes, so there will be co-volcanic ionospheric disturbances, and I will not talk more about this, but they can generate both acoustic and gravity waves because eruption can be preceded by an explosion, and then the eruption itself will generate quasi-periodic variations. So these disturbances will have slightly different characteristics. They will have different velocities, different waveforms, different frequency content. And what we've learned recently is that they will carry the information about the parameters of the source, which means that if we analyze the parameters of the disturbances in the ionosphere in near real time, we reconstruct the parameters of the medium of propagation, which means the background, the atmosphere and the ionosphere, we can imagine to reproduce, to invert the parameters of earthquakes and tsunamis. So which parameters I'm talking about? So for tsunamis, the most important parameters are the wave heights and the velocity of propagation, because this is what we need for alerts. And for earthquakes, we need to know about the source, so we can try to see about the uplift, about the magnitude, I don't know, dimensions of the source, and things like this, because it will always be reflected in the parameters of the disturbance that we detect in the ionosphere. Yes, so here I'm forgetting to say that this branch of science that works on analysis of disturbances related to natural hazards is often called ionospheric seismology. So I will first provide a couple of examples about ionospheric response to earthquakes and the tight coupling that exists between the disturbances in the ionosphere and the earthquake parameters. So the first detection of coseismic ionospheric disturbances was done by Davis and Baker, who detected rather strange signatures in the ionozones in Colorado. And close analysis showed that these disturbances came from March 1964 earthquake in Alaska. But it wasn't until 1995 when French scientist Calais and Minster made the first detection of coseismic ionospheric disturbances in GNSS TC data. And this is where I would consider the opening of the era of modern ionospheric seismology, because currently we have a lot of GNSS stations in tsunamigenic and seismic areas. And with this development, we have learned a lot about coseismic ionospheric disturbances. So first of all, the waveform, then the time of when we can detect them, and then the fact that starting from magnitude 6.6 roughly, maybe sometimes rarely it can be even lower, but it is very likely that we will see the signature in the ionosphere. And then one other important point is that there are actually two main types of coseismic ionospheric disturbances. One will be related to the uplift itself, the displacement of the ground, and they will generate acoustic waves. And then there will be a Rayleigh wave that are seismic wave. They will propagate across along the surface and will generate also N wave. And so in this case, we can see, especially for much stronger earthquakes, we can see these signatures very far away from the epicenter. So like, for instance, these signatures, the first ever signatures observed, they were most likely related to the Rayleigh waves. And also the fact that the Tohoku earthquake was also detected in Europe. Okay, so then very important information is about the fact that the larger is the earthquake, and actually any natural hazard, the larger will be disturbance in the ionosphere. So if we take a look on the amplitude of coseismic ionospheric disturbance, and we analyze different cases, different detections, we will see that it scales with the magnitude, with the uplift, and also with the seismic energy. And this gives us an important possibility for future inversion of earthquake forcing parameters from the ionosphere in near real time. So then there was also another very interesting demonstration that is called ionospheric imagery of seismic faults. So I'm going back to this 2011 Tohoku earthquake that, as I mentioned previously, produced multiple segments of the uplift. And this was all this source of tsunamis. So it will also be source of the ionospheric disturbances, and we can see this in the areas with good coverage, like in Japan, when, you know, if a satellite is passing over the epicentral area. So here, each point corresponds to the intersection point between the line of sight between the satellite and the receiver and the ionosphere. So this is a geographic map, and color shows the amplitude of the TEC. And what we see here is the occurrence of these two segments of an enhanced TEC, which is very close to what we see on the left from seismological models. So what is important to note here is that potentially it's possible to see this information in only 520 seconds after an earthquake occurred. So yes, there is a huge potential for imaging of seismic faults, and of course for the tsunami warnings, because if we see this structure in near real time, this will be a very strong indication on the magnitude, on the immense magnitude of this earthquake, and immediately we understand that a tsunami was generated indeed. So then I'm moving on to ionospheric response to tsunamis. So the first, first it was predicted, this kind of disturbances were predicted by Heinz in 1960s. And it was not until 2001, I believe, 2005 actually, I believe, when French scientists Juliette Artroux and Philippe Lognonet used data, GNSS data, and showed signatures of tsunami that was generated in Peru, in South America, and arrived in Japan. So this was also a breakthrough. And since that, the tsunami ionospheric signatures were detected many times by different research groups around the world. And we've learned that, yes, it's a quasi-periodic signal. We know that it can arrive before or after the passage of tsunami generation. It's still under the debate, and the time as well. So for the information that we have now, tsunamis with wavelengths, with wave heights about 2 to 3 centimeters in the open ocean are very very probable to detect in the ionosphere. by using either receivers on islands or on the coasts. And it is also suggested that the velocity of the tsunami ionospheric disturbances should match the velocity of the tsunami. So this is where the interest is. If you detect these disturbances on islands, you can do the forecast for the coasts. And also for tsunami ionospheric disturbances, they can be detected in the near field, which means very close to the epicenter, and as I just mentioned, in the very far field, like after it crossed the ocean already and arrived on the opposite coast. So here is an example of detection of tsunami ionospheric disturbances, and actually all disturbances here in one. So this is once again the Tohoku earthquake. So the figure on the left is what we call Hodocron or travel time diagram. So here is the distance from the epicenter and the time, and the color shows the amplitude of the TC. So what you can see here is the occurrence of different types of disturbances that lasted for many hours after the earthquake occurred. And on this type of diagram, you can also see the velocity, because the inclination line will show you the velocity. So you see the Rayleigh waves, so this is the fast component. You see the acoustic waves here, and you see slower waves, right? So this is the ones that correspond to tsunamis, and they occur about 30 minutes to 40 minutes after the earthquake. Then for the far field, I'm going back to this first detection. So tsunami was generated here around Peru coast. And about, I think, 20 hours after it was generated, it arrived in Japan here in this direction. And this is what we see. So the time is matching, and also the direction of propagation is matching. These structures are the tsunami ionospheric disturbances. We definitely see multiple positive and negative phases, so it was a quasi-periodic signal. So everything matches. It should be tsunami ionospheric disturbance. So yes, we definitely see the potential for monitoring tsunami propagation from the space. So now, how about measuring tsunami wave heights from the ionosphere? And there were not so many works about this so far. I will only show the first one, which belongs to my colleagues, where they used the normal mode summation technique, and they managed to reproduce tsunami waveforms for three tsunami cases. So as you can see here, the observations are shown in black, and estimated wave heights are shown in red. And the conclusion is it is actually possible to do this potentially with the error less than 20%. So once again, there is a potential for assessment of tsunami wave parameters from the ionosphere. We also know how to estimate the velocity. So there is a potential, but about a couple of years ago, maybe 2-3 years ago, maybe 4, we were at the stage where we had a lot of demonstrations of how the ionospheric measurements can be used, but we didn't have anything that could be just adjusted and used immediately in near real time. So this has been our main work for the last years, developing of tools and methods for real-time operational work and for improvement of the tsunami early warning systems. So as far as how it can be really useful, so I'm summarizing in 2 slides. So I personally see 2 scenarios. First is what I call near-field scenario, where we are using data, let's say, not far from 800 kilometers, because this is how long we can go, how far we can sound the ionosphere from one receiver. So let's imagine, so it's the Tohoku earthquake scenario. So an earthquake occurs, we are about 500 kilometers from it. So we're using data on the coast, and we try to see the source structure. We can estimate the magnitude from our dependencies, and we can try to estimate the vertical displacement. Anyway, what we can see, as I demonstrate also the waveform, everything can help us to understand whether earthquake was big or not. So from this, in this definition, in this scenario, our definition of near real time is less than 15 minutes. As I'm showing here, so an earthquake occurs in about 2 minutes. We will have estimation from seismic data, estimation of the magnitude and the location. In about 7 to 9 minutes, we will detect the disturbances in the ionosphere, and then we'll have about 7 to 8 minutes for our ionospheric methods to work. And the idea is to provide a solution in under 15 minutes after the earthquake occurred. So it will leave us some time. It's difficult to say how much exactly, because it will always depend on the case, how far the epicenter was and the source was. But considering, once again, the Tohoku case, it's about 20 minutes before we alert or not, we take the decision whether we alert the population or not. And scenario number 2 is the far field, where we use data GNSS receivers on islands, and we monitor propagation of tsunamis in open ocean. And very importantly, we don't care about the origin, because once we detect the disturbance and we confirm it's tsunami one, it doesn't matter. We can estimate what we want, and what we want is tsunami wave heights and the propagation speed. So in this scenario, we have much more time. We have much more time. So let's say an earthquake occurs, a tsunami is generated, and it propagates, it generates disturbances. And yes, I put 55 minutes, but it's possible. It depends really where we're detecting, how far we are from the coast. So we can provide our solution before the tsunami continues to propagate and rise to the coast. So this is how I see this usefulness. So I will submit this paper soon. So please take a look if you want. So then the question is, where are we now? And here, as us, I'm referring to the community. And I would like, first of all, to show you, I don't know whether you are aware or not, but currently, to my knowledge, there are 2 main systems that are being developed. So first one is the Guardian, which is the JPL NASA system that has basically exactly the same aim that I've just mentioned, but mostly scenario number 2. So the detection of tsunamis, detection and monitoring of tsunamis. So here on the left, I'm showing their data that are already available in near real time. So you can check their webpage, and I think it's the DIS, the database, where they put all the data that are available. In this case is for the Kamchatka earthquake that occurred 2 weeks ago. So they started with the primary interest on the Pacific, but now, as you can see, it's extended to many more stations, which data can be available in near real time. So the other system is our system, Go Eureka, of which I'm the PI. So it's a collaboration between several research institutes in France, Italy, Norway, and Brazil. And we are willing to have both scenarios in our system. We do not have the web interface yet developed and available for public. But we have developed recently multiple algorithms that can be used immediately already. So which steps should be performed for our system to work is first and foremost, of course, is the automatic detection of these co-seismic and co-tsunamic disturbances. So we are currently, up to now, our group, the Go Eureka group, we developed 5 methods. Mostly they are for co-seismic disturbances, and 2 other methods are coming. So I will only, yes, so we are currently at the first lines, but we are progressing. So I will first talk about the detection, and I will only show just one example because so this was the first actually method that detected ionospheric disturbances by using machine learning. So it's called AID, which in French means help. So it's an algorithm that is using random forest as an algorithm to classify whether the perturbation that we are detecting, if we are detecting is, yes, whether the perturbation can be characterized as perturbation or noise. So it's 50% chance, but there is an algorithm to estimate that. So I would like to point out that this is a supervised machine learning, and this algorithm was trained on real data, so on co-seismic ionospheric time series. So it also estimates the arrival time. So what you can see here is an example of how the algorithm works. So these are the real data, the TC for hours of data. So there is a window. So algorithm moves the window, shifts with each time step. And the window is, I think it's about 700 seconds. So it shifts with time. And when it contains the disturbance inside the window, this is where the detection probability starts to increase. Okay, and then it estimates the time. So here you can see the time that was estimated by human in the training, and the time that was estimated by the algorithm. So this is how this algorithm will detect disturbances and put the points of detection. So on the left, you can see, so these are unlabeled data. So this is the validation step. So this is this earthquake that occurred in Chile. So you see the epicenter, the source, and this is where our algorithm detected co-seismic ionospheric disturbances and put the points at the time of detection of the disturbance. And the color shows the time. So as you can see here, the first disturbance occurs right on this side next to the co-seismic uplift, and then it goes away from the epicentral area. So basically we have our information about the source, while we don't have any information about the source from the seismic region. So it's fully done based on the ionospheric measurements and our algorithm. There are, of course, a lot of tricky points that we are working on. For instance, the altitude that we are taking, the altitude of the ionosphere, because in GNSS sounding, we do not know exactly which altitude we detect. But once we overcome this has a very great potential for tsunami early warning system improvements. So the second thing that I would like to talk about is the confirmation of the origin of the disturbance that we are detecting. So I mentioned this previously, and I'm sure many of you know this very well, but the ionosphere is an extremely variable medium. There are always different types of disturbances that can propagate, driven by different sources, from above, from below. And it is probably a little bit easier for earthquakes because to confirm that this disturbance is an earthquake, because of the waveform is very often N wave, and there are not so many other events that can generate this type of wave. And also it can be of very high amplitude. But for tsunamis, it can be very tricky to prove that this disturbance is the one that is driven by tsunami. The direction should match, the time should match, and also the problem is that this quasi-periodic waveform is very common, and also tsunamic signatures can have rather small amplitude. So this is a challenging one. And this is why we have developed recently a tool that can identify the source of ionospheric disturbances in near real time. So our approach is based on analysis of spatial temporal characteristics of ionospheric disturbances from known sources. So this is where it's a game changer, because in our group, we have rather vast experience on knowing, on studying characteristics of different types of ionospheric disturbances, and they will be different. So then the problem was to make it work in near real time. As I said, in the post-processing, we have time, we have everything, we have our tools already developed, so it all works. We know how to distinguish, but how to do this in near real time? So the idea was to develop first methods that will allow us to estimate spatial temporal parameters in near real-time scenario. And by that, I mean the parameters will be the frequency content, which can be done. The horizontal velocity is a very important parameter because it will be different for different types of disturbances. And also, I will not explain this in much details, but the sort of locality, because we also know that disturbances that are driven by earthquakes and some other point source types of phenomena, these disturbances will be more or less localized. And then tsunami disturbances that are driven by tsunamis, they will be propagating with a very or much larger wavefronts. It will be more like a plane wave. So if we analyze this kind of locality of detections, like how local this disturbance and how they propagate in like outward circle wave or a plane wave, then it will also give us a hint on the origin of the disturbance. So with this, I'm going back on the left side. So in this first attempt to classify and identify, to classify disturbances in real time, we only had 6 classes. Earthquake, tsunamis, volcanic eruptions, and explosions that normally, by the way, should be separated. Then we had tornadoes, we had rugged launches and explosions, and we had plasma bubbles. So I know it's slightly unexpected, but it's because we looked in a near real-time scenario, and we found that plasma bubble signatures can look like disturbances that are driven by natural hazards, but they will be very different. I will prove this later. And then in this database, we analyzed 33 events, which in number of line of sights is a very huge amount, actually. So I will not have time to develop more about this algorithm, but just to show the results and the examples. So for instance, these are just results of analysis of 2 parameters, main parameters, so the frequency and the horizontal velocity, done by using our near real-time applicable methods. So we show that the frequency, we have low frequency signal. So for those who know, usually in post-processing, tsunami ionospheric disturbances will have about frequency about 1 millihertz. Here in real time, it will be slightly high. It depends on the method that you're using, but this will be a main change. And then, but it will be changed for all disturbances. And then for the velocity, it's the same. So once again, a near real-time compatible method estimates the mean velocity to be about 270, which is very close to what we usually see in post-processing. So basically, just once again, when we develop an algorithm for a near real-time, we have to learn all these parameters once again in near real-time tools. So this was something that we've discovered, and it was very interesting to do. So, and then earthquake, you will see there is a huge difference in frequencies and also in the velocities, very close to what we know from post-processing. And then we had done this for all the events for 6 classes. And we had actually 6 diagrams of 4 parameters, of combinations of 4 parameters. So I'm so sorry for not so good explanation, but it's just for the matter of timing. So in this diagram, which we call our dictionary, so for real-time disturbances in their parameters. So here I'm showing the frequency versus horizontal velocity, because this is one of the most one of the clearest differences between the parameters of different classes of disturbances driven by different sources. So in red, for instance, is earthquakes. In green are tsunamis. Volcanic eruptions are shown here in orange. So then you have rocket launches and explosions that will be very close to earthquakes, which is also known from post-processing. Then we also have tornadoes that will generate two types of different signatures, gravity waves and oscillations. And also, finally, the gray one is the plasma bubbles, very different. So it will be very helpful, because when you look like on the time series, it can look like, oh, maybe there is an earthquake. So this is a nice diagram. We had 6 of them. Some of them were not very useful. We are testing, we are looking at, we are developing, we are improving, we are learning. But it's very promising. So now how we apply these algorithms, and we'll see what's happening. So one of the first cases, it was the earthquake that occurred on the 1st of January of 2024, magnitude 7.5, which is not very strong earthquake from a ionospheric point of view. So you will see a small disturbance here at about 7:20. So time is shown here, and this will be the TC. Actually, the TC derivative, this is what we are using in real time, near real-time approach, to remove the trend. And the problem here will be, as many of you know, I'm sure, as the fact that earthquake occurred at 7:10 universal time, but in Japan, the local time is evening, which means that a terminator is coming, right? And terminator is known as the source of TIDs. And you will see here, when I run the video, you will see here the occurrence of these structures. Here, you see the TIDs, structures. They're very close to the epicentral region. And here are the co-seismic ionospheric disturbances. Once again, structures here and co-seismic ionospheric disturbances. So this will be a very realistic case. This is what the ionosphere looks like. And this is how challenging it can be to use the ionosphere for these purposes, and how careful we should be in developing, in taking into account all of this when we develop our ionosphere-based methods. But I have very good news. Our methods worked. So here is a timeline. An earthquake occurred, and theoretical predictions, the NRLMC's model says that on that day, acoustic waves would take about 8.5 minutes to reach the altitude of the ionosphere. And our methods detected these disturbances in the ionosphere. And in addition to this, in below 10 minutes, we already had estimated the velocities of propagation of disturbance. And the direction shows the direction of propagation of the disturbance, as you can see here. And from the video that I've just shown, we also see that it is correct, both the velocity and the direction of propagation. So yes, this is a good result. And another good result, that in about 12 to 15 minutes, our algorithm will put this disturbance very close to other previous earthquakes that were already in our database. So in about 12 minutes, we can say, yes, this earthquake, can confirm this disturbance is driven by earthquake. Then one other example is just the recent Kamchatka earthquake, which, as you of course know, also generated a tsunami. So I will not be able to show the figures here because of some reasons. But in near real-time scenario, our methods that were recently developed, they detect co-seismic and co-tsunami ionospheric disturbances. And they were also able to confirm the tsunami origin of the ionospheric disturbances in different places in the Pacific Ocean. So especially in Hawaii, that had a huge tsunami. So this, I guess, I tried to demonstrate that ionosphere holds a huge potential for natural hazard assessment, also in near real time. So we have developed, and also the community, I know that the Guardian team, they also working very actively on this, developed the first methods that allow detection of coseismic ionospheric disturbances and some other disturbances as well. So there are always peculiar, tricky things that we know as, experts on the TC data, but we are working on this. So we have tools for automatic detection. We have tools for determining the arrival times, and we also learned and developed tools for estimating, to estimate the velocity in near real time, the direction of propagation. So all this is already a big step towards the near real time use of ionospheric data for natural hazard assessment. So yes, we also have this method, the first attempt. We will work on this more to have more classes to know more about the disturbances that will help us to confirm the link of the relation of this detected disturbance to natural hazards. Yes, we are developing methods for allowing for inversion of earthquakes and tsunamis parameters from the ionosphere. We, for the Go Eureka for our European system, we are starting tests on real-time TC streams later this year. And of course, the future satellite data, either imagers or, I don't know, perhaps constellations, if we are talking about density, the constellations will be very useful. And this will be it. Thank you so much for your attention.
Yeah, thank you so much. I think this is a very interesting talk and informative. And I think you're very, very advanced and far ahead of many people. Congratulations.
Thank you.
Yeah, and then I see a number of experts in this in the audience. Do you have any questions? I don't know. Is Sato-san, you still there? You are Professor.
Yes, I'm here.
Yeah, you have questions. Yeah, because Professor Takahiko Sato, he is the president of AOGS, and he is all our boss. So his comment or question will be very important.
Yeah,
Sato-san?
although I'm not an expert about ionospheric disturbances, but you mentioned the terminator in the case of Noto earthquake on 1st of January 2024, that the approaching of terminator had some effect on the observability of disturbances. So that, is there any other way of eliminating such effect by for example, by using different frequencies or something like?
You mean like filtering?
Yeah, something like that.
Yeah, okay. So in the case of like near field scenario, so we don't have much time to use like bandpass filter that we usually use because we need to stack a lot of data to, like, I don't know, if you want to filter, then you need to have this data and we don't have time. And that is why we went to the TC derivative. We switched to TC derivative. And so I think the discrimination will be to study more the terminator-driven disturbances. And usually they will have slightly different velocity and different direction of propagation. And that's why one of my main ideas was to use, yes, to determine these parameters like the velocity, direction of propagation, because this will be one of the keys to help us to discriminate. So because filtering, I'm not sure it will, I mean, in the like very short time, it's not possible to apply the bandpass filter. Perhaps some other decomposition filtering, for instance.
Okay, thank you. Very clear. Arigato.
Arigato gozaimasu.
Good. And Professor Haisha Liu. you have some questions?
I'm neither an expert of this this is a tsunami warning system. I do have a friend whose PhD topics about this. Sorry, I don't have a specific questions about your talk. I need to learn about that. Yeah.
Okay. Very good.
But I know I did some work about the vertical TEC, the second derivative of the TEC. This kilogram pulse. Yeah, I did have a little bit experience, and I know the automatic detection of these different waves is very challenging.
Yes, it is. Yeah.
Yeah. Congratulations.
Oh, thank you. Yeah, we had to add additional steps to confirm the detection as well in our first method.
Yeah, usually for post processing, we can rely on
yes, exactly.
Yes. Yeah. So I know this is a very challenging topic in near real time.
Yes.
Yeah. Thank you.
Thank you.
If you have questions, you could either raise your hand or just ask. Yeah,
I think there was a question in the chat.
Is that right? Let me see.
There was something about the precursors.
Can you read it and then you can?
Oh, okay. How can ionospheric TC anomalies potentially linked to earthquake precursors be distinguished from variations caused by solar geomagnetic activity? Oh, okay. So I haven't talked here about the precursors, and I really didn't work on that. So precursors is a very controversial subject, and it is very difficult. So as I said, many different disturbances can be driven by different phenomena. So it's very difficult to prove this is related to precursor. So in the case of co-seismic disturbances, it's easier because the physics is there and it's related to this earthquake. And you can see how it literally comes away from it. So it's a different physics, a different phenomenon.
Well, your goal, the Go Eureka project that you're the PI, is mainly focused on Europe, right?
No. Actually, it's funny, but we don't have this interest. We don't have earthquakes and tsunamis. I mean, we don't have tsunamis. We will be mostly focusing on regions like Pacific and regions that, like I think one of our first interests is New Zealand and Japan and Sumatra. So we contacted them. New Zealand said you have an access to real-time data right away. In Japan, it's trickier, and Sumatra will also provide us the access. Maybe in Taiwan as well, we can have an access to real-time data.
Is it the GNSS system or what?
We need GNSS. We need dual frequency GNSS receivers. Yeah, it can be 30 seconds, but ideally, like higher rate data will be even better, but it's very expensive, we know. Because like for imagery, 1 hertz data are better than 30 seconds, even for detection, for everything. But send the data every second, it's very like expensive. And it's also, yes, it will take a lot of space on our computers as well.
So this project already in place, right? For how long?
Okay, so it's been our like 3rd year. It's a little bit trickier than that because we don't have an official project, but we are a team of different projects. So we are responsible for different types of different parts of the project. So for instance, my team at IPGP, we developed the algorithms for detection, for spatial temporal characteristics. So currently we're developing a database for tsunami, called tsunami ionospheric disturbances, like to have also a probably AI-based algorithm to detect them. And then I have colleagues who will be more instrumental part, like because we also need to check the data in real time, and yes, to really have them access, like really instrumentally having access to them. And we are building an interface. So sort of USGS earthquake webpage, but for ionospheric seismology, something like that.
Mm-hmm. Okay, thank you. Thank you very much. Other questions to Elvira?
Yeah,
Please, Veronica. Yeah,
hello,
please.
Professor. Really nice talk. I'm just curious about the data set you are preparing. Are you going to include, I mean, like for a part of the typical ones that's caused by seismics? Well, it's also an earthquake, but just curious about the outliers like the 2018 Palu earthquake and tsunami. Are you considering that as well?
Okay, so far I don't think we have it, but the main idea is to study all of them that produced a significant signature in the ionosphere. So yeah, maybe if it's like really an outlier, yeah, but we need to study this, because if in real time there is another outlier, we need to think about it. So we don't really want to completely remove it, but just to know it is an outlier and why it is an outlier.
Okay, thank you so much.
Okay, so it's almost 5 o'clock. It's 1 hour, and I think that we will put this video on the web page, also on YouTube, so that everybody could watch it afterward. And I actually encourage the expert to watch this video, because it's very, 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 very informative. And then I want to thank Elvira for this very nice talk, and I hope to see you in next year in Fukuoka.
I will yes, I would be delighted. Right. Yeah.
And we will try to organize a session. I think that your work will be one of the highlights of the session, I'm sure. And Haisha Professor Liu, she's organizer of this ionospheric working group. So she would obviously would contact you, very soon.
Okay.
Yeah, sure.
Yeah. And thank you again, everybody.
Thank you. Nice to meet you.
Have a nice evening in Taiwan, and good day in.
Thank you. Yeah, thank you very much. Bye.
Thank you.